Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 42, Electrochemistry Part 2. Here are our objectives for today's video. Pause here. So a galvanic cell is essentially a battery of sorts. It's just a single cell battery. And this is where we combine an oxidation and a reduction reaction. So the anode of the galvanic cell, that is where oxidation occurs. And the cathode is where reduction occurs. There's not really to me, that seems really counterintuitive. Cathode, we typically associate cats with positive, but that just kind of needs to be memorized. Galvanic cells, they are used to convert chemical energy into electrical energy. And in order to have a galvanic cell, if you just have a oxidation in one beaker and a reduction in another beaker, and you don't have anything between them, nothing is going to happen. And that's because for an oxidation reaction, you're probably producing something that has a positive charge. For example, Fe3+. It's going to need a counter ion in order to balance it. So a salt bridge is literally just a piece of plastic that has some kind of salt in it, and that one end is in the anode and one end is in the cathode. We're going to be looking at pictures of these as we do examples with this. A porous disk does the same thing. So it says allow electrons to flow in the notes, but that is more of the conceptual sense of electrons. It's typically ions that are actually flowing. So I would add to your notes electron/ions. Pause here. So to determine the voltage of a cell, we're going to have standard reduction potentials. They're typically given in a problem, or you'll have a table of them. These are actually measured values. So when we compare the reduction of hydrogen to something else, the difference between those two reactions is the standard reduction potential. That part, admittedly, is not super important. What does matter is that we can use these values to determine the voltage of a galvanic cell. You're sometimes going to hear it called electromotive force. That's what I meant by EMF in the third bullet point. It's something called an intensive properties, meaning that the mole-to-mole ratio, it's not going to affect E cell. We're going to take a look at what this looks like in the context of a calculation in a moment. Pause here. Right, so to determine cell potential, it's pretty straightforward. You add the value of the oxidation to the reduction. You're going to end up changing the sign for the oxidation because you're reversing the reaction. And then you want a positive E cell. The more positive it is, the more thermodynamically favorable the reaction is. A negative E cell is not thermodynamically favorable. Pause here. So when I look at this, I see that I need to reverse one of my reactions. So 0.77 volts, that's super positive, so that's super favorable. And 0.34 is also positive, also favorable, but less so than the first one. So this is going to be my oxidation. And then for my reduction, I'm actually going to need to reverse the reaction. And my new E cell is just the negative of that. So I have to pick one to reverse. My overall balanced chemical equation, I just need to make sure that I've balanced out my electrons. So hence 2 Fe 3 plus aqueous plus Cu. It's going to be a solid. 2 Fe 2 plus aqueous plus Cu 2 plus aqueous. So actually, I'm going to need to add another 30-second video on at the end. So I'm going to stop here, but then I'm going to continue in the next one.